continue with stochastic calculus. We now move on to stochastic differential equations. Um, so first off, I have treated differential equations, in the classical sense, and I have several videos on that on my channel already. So, but this is us talking about stochastic differential equation for the first time. So, a stochastic differential equation, SDE, is a differential equation that includes randomness, and the general form is dx sub t equals mu of xt comma t dt plus sigma of x sub t comma t dwt, right? Where x sub t is the stochastic process, then mu of xt comma t is the drift term, and then sigma of x sub t comma t is the diffusion term, and wt is the winner process, the Brownian, which is also known as Brownian motion. So, as a refresher, again, we talk about the winner process of Brownian motion. A winner process W sub t satisfies W naught equals zero. That means at time zero, the process is zero. Then it has independent increments, and then Wt minus Ws is normally distributed with mean zero and t minus s as variance. That's literally the difference between the time steps. And then we have continuous parts, but nowhere differentiable. The reason why stochastic calculus is useful in the first place is because it is nowhere differentiable, meaning that the w dt does not exist. So, and it has one key property in Ito calculus, that dw sub t squared equals dt, like that. So now the question is, why the classical calculus fails in this case? First of all, Brownian motion is not differentiable because it is nowhere differentiable, right? The WTDT does not exist, like I just said. Instead, Ito calculus defines that the W sub t squared is equal to dt, like that. So that's what we have, like that. So then we've always talked about the Ito's lemma. If the xt is mu dt plus sigma dwt, then for a function f of x sub t comma t, df will be df dt plus mu df dx plus half sigma squared d squared f dx squared dt plus sigma df dx dwt. I mean, we've encountered this a lot of times, and of course, this is just occurring this way because of the rearrangement of whatever substitution would have come in along the process. All right, so as you can see, this one only has terms in WT, meaning that we have taken care of x of t to we have replaced we have substituted with this, and that's why we have this long one. So df dt, as you can see, mu df dx dt, then half sigma squared d squared f dx squared dt plus sigma df dx dw sub t. So example one, we have Brownian motion with drift. So here we have dx sub t equals mu dt plus sigma dw sub t. And if you solve this, the solution is x sub t equals x naught plus mu t plus sigma omega t. I mean, for obvious reasons, it's more like if you substitute, it's more like you just apply integral to everything, right? So if you integrate xt. Okay, well, I think I may even want to consider, just playing with that, right? So you have dx of t, dx sub t equals mu dt plus sigma dw sub t. So that's the kind of thing you have here. And since we learned in the previous video that it follows linearity, so if you just integrate, so you have dx sub t, of course, from 0 to t is equal to mu integral of dt. Of course, mu is constant, plus sigma integral the omega t from 0 to t, like that, 0 to t again. I hope that works. Let me see. Okay, or maybe we don't even bother in the first place, right? Yeah, we just apply to this, or only this one. Okay, so we then have this is integral of the x of t. That will be x of t, you know, um, x of t from 0 to t, and that is mu. When you differentiate t, you get integral of dt is t from 0 to t again, plus sigma d omega t, that will simply be omega t from 0 to t. So that means here we have x t minus x naught equals mu t minus 0 plus sigma omega t minus 0. Okay, so that's like xt minus x naught equals mu t plus sigma wt. I've been calling that omega. It's not omega, it's wt. So that xt now is then x naught plus mu t plus sigma w sub t. So that's the kind of thing we have over there. But of course, the big T has not been replaced. That's why it keeps looking like this. So that's the deal. So we can then simulate, we can, you know, run that, and we get Brownian motion with drifts as we have it right here. So you see, this is mu t plus sigma w. So mu has been given as 0.5, sigma is given as 1.0, then t and all of that, all of that, all those ones have been defined, right? So, and of course, as usual, as you keep running, it keeps changing like that. Then we have geometric Brownian motion. Interestingly, I think in the next video, we'll be looking at geometric Brownian motion in some depth. So if you have the x sub t equals mu x sub t dt plus sigma x sub t dwt. So the difference is now that we have x sub t added to this. So if you solve this, it ends up being x sub t equals x naught exponent, all of this now. So we have all that. I mean, if you see what's happening here, um, if you factorize out x of t, you can collect like terms. So you have the x of t over x of t, and that will go into mu dt plus sigma, blah, blah. So if you do all of that, you get this solution, x of t equals x naught exponent mu minus half sigma squared t plus sigma omega, w sub t rather. So we can simulate that actually. That is defined in line 12 right here, having fixed all the other parameters. So if you run that, we have this geometric Brownian motion, which we are going to see fully in the next video. Of course, it keeps changing too as we keep running, it keeps changing. That's a geometric Brownian motion. Then we have some numerical methods for solving stochastic differential equations. So exact solutions are rare for stochastic differential equations. So we use approximations like the Euler-Maruyama method. So that's given as xn plus 1. So it's like Euler, but infused with randomness, as we see the winner process here, or the Brownian motion process here. So xn plus 1 is xn plus mu xn comma tn dt plus sigma xn comma tn delta omega w sub n, where the change in w sub n is normally distributed with mean zero and variance change in time, right? So that can be simulated this way. So you just fix up those define dt as t over n, x is zeros, that's a kind of initialization. So you are defining the function called Euler-Maruyama that takes mu sigma x naught t and n. So you have all of that here. And you have dw defined here, where xi will now be defined according to what the formula looks like. So you have xi is now xi minus 1 plus mu xi minus 1 times change in time plus sigma xi minus 1 times dw. So you now have some examples now. So you can now have a mu function which is 0.1x, sigma function 0.2x. So it means even the sigma and the mu itself, they are given as functions. So you can then run all that and you keep having different shapes like this. So you keep having, so for the Euler-Maruyama approximation, you have that. But if you want to have a fixed result, you may need to set a seed, which makes sure that the results don't keep changing. So that's one numerical method, the Euler-Maruyama method. And then we have the Ornstein-Uhlenbeck process. Ornstein-Uhlenbeck process. So this stochastic differential equation is given as dx of t equals theta into mu minus xt dt plus sigma into dw sub t. This is a mean reverting process, and that can be given. So you define theta, the value of mu sigma x naught, and then so again we bring in the Euler-Maruyama, except that, so for Euler Maruyama, there was nothing like theta, but we have theta coming up in this case. So we define the mu function theta times the value of mu minus x. That's theta into mu minus x now. That's what we have like right here. So that's the modification that the Ornstein-Uhlenbeck process adds to the Euler. So we then call the Euler-Maruyama still, you know, and then so we bring in the mu and sigma functions defined instead of just assigning the mu and sigma like we did previously. So we throw them directly into this. Okay, we also have mu and sigma functions here, interestingly. uh okay, so we then have the Ornstein-Uhlenbeck process as we have it here. So like we noticed, right, it's the mean reverting process, so that's why you see it's always on the decline, right? It's always on the decline, like that. So mean reverting. So in 5.51.7, we see Ito versus Stratonovic, right? So the feature is that uh, the calculus, Ito is modified, Stratonovic is classical. For chain rule, it's adjusted in Ito, but in Stratonovic, it is standard. You have the Ito application in finance and Stratonovic application in physics, like that. So we can look at an example. So imagine example 3, dx of t equals 2x of t dt plus 3x of t dwt. So step 1, you need to identify the parameters. First of all, mu is 2 and sigma is 3. Then if you apply the GBM solution, which is this x of t that we saw before, the this okay, this is the GBM solution. You have your x naught, so you just apply the solution, just fix up this in the expression. All right, so you then have x naught exponent 2 minus half times 3. I think that's where sigma squared comes in, right? T 3wt, and then xt. Now if you tidy things up a little bit, this is 2 minus 4.5, right? That's minus 2.5 plus 3wt, and then you have that. So you can then simulate to get the answer and all that. So we have some practice problems here. I'm going to solve, I think, um, okay, let me see. I'm going to pick one or two of them to solve. So question 10 and then question 20. Question 10 and question 20. Question 10 is solve the dt 0.1 xt dt plus 0.3 xt dwt. And of course, we have all these Euler-Maruyama things here. And then we have question 20 also. So consider the x of t equals x sub t squared dt plus x sub t dwt. Apply Ito's lemma and simplify the resulting expression. So let me flash the questions again and then go over to solve them, to solve the two I've chosen. So define a winner process W of t and list its main properties. So you remember those four properties, starting with W of 0 equals 0 and all of that. Show that the Brownian motion dwt squared is dt. Explain why wt is nowhere differentiable because it is stochastic. So you have 1, 2, 3, 4, 2, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you have 10, 11, 12, 13, 14, 15, 16. You have 17, 18, and 19. So try your hands on them. So let me go and take care of questions 10 and 11. Questions 10 and 11. Question 10 and 11. So starting with question 10 now. So we have this. We want to solve the stochastic differential equation. The x sub t equals 0.1 x sub t dt plus 0.3 x sub t dw sub t. So we want to solve that. So the first thing we want to do, step 1, we need to identify the type of problem it is. Identify. So how do we identify this? There's xt here. If there's no xt, then it's regular Brownian motion. But because of this xt we have it, then it is geometric Brownian motion. So we say this is a geometric this is a geometric Brownian motion. That's GBM, GBM. So, and in that case, that means it looks like dx of t equals mu x sub t dt plus sigma x sub t dw sub t. Okay, so if that is the case now, it means we can say this is mu, and this is sigma. So mu is 0.1, sigma is 0.3. So mu is 0.1, sigma is 0.3. So with that in place, then we can have we can go for step 2, where we use known solution formula. Known solution formula. So the known solution formula is this: x sub t equals x naught exponent mu minus half sigma squared t plus sigma w sub t. That's the known formula there. So we then go for step 3. So in step 3 now we substitute. So step 3, substitute values. Substitute values. Okay, so we have this chunk here first of all. So for that chunk, right, we have mu minus half sigma squared. Mu is 0.1 minus half sigma is 0.3 squared. That's 0.1 minus half into 0.09. So that is 0.1 minus 0.045. So that is 0.055. So that's for this part there. So other ones are like straightforward. So step 5 now. Is that step 5 or step 3? Step 3, we have the final answer. Final answer. That means that x sub t is equal to x naught, then exponent 0.055 t, as you see here. So all this 0.055 t plus sigma t, that's 0.3. I mean sigma w sub t, 0.3 w sub t. And that's what we have right there. And that's question 10 answered like that. So we then move on to question 20. So we move on to question 20. So for question 20 now, we have question 20, that's problem 20. Problem 20. So we are given the x sub t equals xt squared plus xt squared dt, actually xt squared dt plus x sub t d w sub t. So in that case now we can let f of x sub t be 1 over x sub t. Now, what is informing this? Let's see the problem again. That's question 20. Apply Ito's lemma to f of x sub t equals 1 over x sub t. We are given that. So you don't just, if you cannot identify it, you'll be given, right? I think we've solved problems for where we could easily identify it from the expression given. So we let x sub t, f of x sub t to be 1 over x sub t. So if that is the case, what do we do then? So we need derivatives. So step 1 here, for step 1, we compute derivatives. Compute derivatives. So that means we have f prime of x. That's like f sub x, like we did before. So of course, if you do this, that's xt raised by minus 1. That's minus 1 over xt squared. You know, that goes. Then the second derivative, that's f prime prime of x. When we differentiate this the second time, that's like minus xt raised by minus 2. That'll be 2 over xt raised to power 3. Yeah, 2 over xt raised to power 3, like this. So with all of that in place, we then identify coefficients. So that's step 2 now. Step 2, identify coefficients. So in as much as stochastic calculus does not uh, follow the classical calculus, but we still need some concepts of classical calculus to get things moving. So here now we identify the parts now. So first of all, our mu, based on the original expression, our mu is xt squared, and our sigma seems to be xt. So mu is x sub t squared, and sigma is xt, like that. Then we move on to step 3 now. Step 3, where we apply Ito's lemma. Apply Ito's lemma. So, and Ito's lemma tells us that df is equal to, so from all we've seen, so that's mu f prime of x plus half sigma squared f prime prime of x dt plus sigma f prime of x dw sub t. So once that is in place, then we can have we can then have the we now put everything we have in place and fix it all up. So we then have the first term now. So see this first term here, that is mu f prime of x. So that is, so already we know mu to be xt squared here. So mu is xt squared. So we have xt squared. Then f prime of x is 1. That's minus 1 over xt squared. So, I mean, this cancels out and we just have minus 1 for that first part. Or if I may write it out more carefully, mu f prime of x is minus 1. We have that stated. Then for the second term, so this is the, so for the second term, right, we have all this. So for the, this is the first term, right? No, no, no. I think I overstretched. So this is first, this is the first term here. This is the first term. So for the second term, we have this. So second term, that is half sigma squared f prime prime of x. So that is half sigma squared as xt squared, because we know sigma is xt. So sigma squared is xt squared. Then f prime prime of x is that expression. That's 2 over xt cube. That's 2 over xt raised by 3. So 2 cancels 2 here. 2 of this cancels this. So we have 1 over xt for that second term. So again, we have half sigma squared f prime prime of x to be 1 over xt. So that is in place. Then for the drift term now, for the drift term, where's the drift term here? That's okay, for the drift, for this whole part here. So this term we have this is minus 1 plus 1 over x sub t. Then for this other part, diffusion term. So let me go like this. So for this term now, we have sigma f prime of x. So that is sigma f prime of x. That is sigma. Sigma is xt as identified. Then f prime of x is minus 1 over xt squared. So one of these cancels this. So we have minus 1 over xt. So that is sigma f prime of x is equal to minus 1 over x sub t. So we have all of that too. So finally, we can then have, so final result now. How many steps did I note before now? Step 3. Okay, so that'll be my step 4 now. Step 4, you have the final answer. Final answer. So we have, what's the expression now? df. What's the expression? So the f is all of these things. and we took f to be 1 over x sub t. So the f, which is equal to, okay, let me not rewrite that. Let me just go straight. So we know f is 1 over x of t, so we just write. So d of 1 over x of t is equal to minus 1 plus 1 over x of t dt minus 1 over x of t minus 1 over x sub t dw sub t. So we have all of this like that. So that's the answer we get there. So with this, we come to the end of this interesting video about stochastic differential equations. Let me know how helpful this is. And if there's something else you'd like me to try out, feel very free to let me know. Don't forget to try your hands on the practice problems. Follow the patterns I have set already. If you have subscribed already, I thank you very much for doing that. And if you have not subscribed, what exactly are you waiting for? Why not go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of the channel by clicking on join. That will give you some special privileges like getting to see some videos first or seeing some videos exclusively because you're a member of the channel. You can also request for PDF copies of my notes. We can hang out together online if you're in the or if you are in the same geographical location. We can actually hang out physically. Um, ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. So, like, come your way again. Keep doing maths right. Bye.